My name is Mohamed, and I'll tell you today about XO. And I will just do it first in a TLDR fashion, like just 5 minutes, and I'll give some more details. In the TLDR version, XO is essentially a library, an open source library that allows you to run AI clusters on everyday devices, like a phone, a laptop, even an Apple Watch if you want. I'll just start with a video demo. Here you see an LLM prompt like ChatGPT. And essentially the whole thing is just running on a cluster made of like edge devices like an iPad, iPhone, and so on. So that's really the TLDR. And XO is just optimized to be installed really easily and just works on the go. If you just like have Python, clone the repo, go to XO, install the shell script, you click on Python and run main, and that's it. That's all you need to know. If all of us today just do this now, you can just have XO running. For example, if I have it running on my machine, I'll just have like one MacBook Air right there. And if anyone else here just does it right now, which we can try later, just installs it, and you're on the same Wi-Fi network, or you're connected in any way, you will automatically be aggregated together, and you can use all the devices to run like large AI models. Like later, for example, if we have time, we could just get all the MacBooks or iPhones or whatever we have here in the room and just run massive AI models together in this cluster fashion. So that's really the TLDR of what XO is. You just can now run large AI models without needing any special hardware like an NVIDIA GPU. Just like any normal like edge device, everyday device can just be used and aggregated together to run things combined. And you can see on the top a bar for how much compute I have, like how many flops I can process and so on. And everything else, whether it's networking, how the model is sharded, how things are aggregated, is just taken care of behind the scenes. You just like run one command and that's it. And because it's so easy to use, XO is quite popular. In like 2 months, it got like 9.9 thousand GitHub stars. And again, using it is really easy. We can just, Python, clone the repo, install the shell script, you'll be in a virtual environment, and then just run XO. And if we do it now, which we can, as I said, we could just like jointly live now run very large models together. That's just the TLDR of what XO is, and probably why I got invited here today. And the rest of my talk is just like some details about why we care about this, the motivation for building it, and some more details about how it actually works and the challenges in building a library like this. I will leave this on in case someone wants to try it and install it for a sec, and then I'm gonna go on with the details. So the initial thing I said was like, oh, XO just allows you to run AI models on any device, but really it's the way I think about it is like, how can we democratize access to AI models? I'm not gonna talk too much about like AI risks and all that stuff. I'm gonna leave that for another talk. I'm gonna dig into the details. But on a very high level, there are two worlds in which we're about to enter. One in which the frontier AI models are open and democratized, and one in which you only have like a handful of AI models, AI companies that control the best models in the world. And well, there are pros and cons for safety and all that stuff for both sides, but I would just like post today that the open world is slightly better. And open source AI is quite different from open source software in a few ways. In open source software, really, you just need a laptop and some good ideas, and then you can contribute. Open source AI is a lot more like hardware, where you need a lot of capital up front even if you make a dent. Like, for example, to create an AI model, to train a model, like these large models by Meta AI, you need like loads and loads of GPUs and massive data centers highly connected. So it's not like if I just had good ideas, I can contribute to creating better AI models. But it's not just that creating models is hard. Even if Meta, which right now are doing us all a favor by open sourcing the best models in the world, or some of the best models in the world, training the model is very computationally expensive, but also just using it, just inference is also very hard. There's one model Meta released called Llama 405B, 405 billion parameters. And that model is open source, and it's very close to performance with the best closed source models like ChatGPT. But just that the model is open source is not enough for me to use it. Actually, to use that model, I need like a rack of multiple of these H100 GPUs, for example. And just one of these is roughly $30,000. So open source AI is different than open source software in two ways. Just working on creating any models is very expensive, but even if these models have been created and open sourced, they're still very hard to run. And today I'm going to focus on the second part. Assuming someone, let's say Meta, has done great work in creating these models, spending all the capital on it, and then open source it for us, how can we actually use it? Because I don't personally have like 8 of these H100 GPUs at home. And, well, you guessed it. The idea with EXO is, well, you can just aggregate any compute you have and just like run models on it. And with that, for example, you get a diagram like this. I can just have a few Macs that I have at home. Well, 2 are mine and 1 of my friend. And I can just aggregate them together and run like any large model without needing all these expensive GPUs and setups for it. And the example I just gave was, for example, Llama 405B. Here's a video just like running it at 2 Macs. They're very spec'd out Macs, so normally you would need maybe like 4.
So it's a 405 billion parameter model. I just got the new Llama running on my 2 MacBooks. So it's a 405 billion parameter model, which is 4-bit quantized. So it's about 200 gigabytes that is split up between these 2 MacBooks. And you can see that it's a larger model.
That's fine.
And it's actually being a little bit sarcastic to me in the responses, which is...
The audio is not being shared, but what's happening here on a high level is just, without needing multiple of these GPUs, I can just like get enough Macs together to run the largest models. And yeah, and actually even Meta like commented on this, that the use of consumer hardware for stuff like this allows us to democratize these AI models further. Okay, so just like a bit more detail about how it actually works and what the challenges are in like building a system like this, and also what the limitations are, because it's not quite the same as having data center GPUs. So first, let's discuss the simplest setting. We just have one device. I just have one Mac or one phone, and I want to run a model. What can I do? There are 2 scenarios. Scenario 1, which the VRAM I have, the memory I have on this Mac, is like larger than the model size. So let's say for this example, I have 16 gigabytes. One model I can run is Llama 8B. It's 8 billion parameters. You can get it in different sizes based on the quantization. Let's say I do 4-bit quantized. That means it's about 4 gigabytes. If I have a model that's about 4 gigabytes and my laptop has 16 gigabytes, I can just easily run on one device. There's nothing crazy here. And I can run a model of any size. For example, I just tried it earlier, and I just like, without any optimizations, I got a quick response at 70 tokens per second. And this applies to any model that fits into memory. We can do something live, for example, where I could just, oh, it's very zoomed out. I can use like any tool, just like run a single device. Like for example, tell me 3 things about the UK or something. And I can just run like a, well, large language model that is relatively small in size, so like a small large language model. And it runs fairly fast, just runs fully on my device, and life is easy. You can see here, actually, this model is even smaller. So I got like 35 tokens per second, I think. What was it? Yeah, 35.5 tokens per second. So back to this example. If I'm trying to run a large model and that model fits into my memory, life is easy. I can just run it on my device. But what if the model doesn't quite fit into memory? Like if it's 70 billion parameters, even if it's 4-bit quantized, it's around 35 gigabytes. It doesn't quite fit on my device. So what can I do? I can still run it on a single device by being a bit smart about it. And on a very high level, any of these models is just like a machine learning model that's consisted of like layers. And these layers just like process information sequentially. Like I give it an input, like my prompt. The first layer will process something, we'll pass the embedding to the next, and then we'll keep going until the end, and then we'll get like a result, which would be a token in this case. Let's just imagine a word. And then you take that, put it to the next model, and keep going until you have like the entire generation happening. So it's just like generate stuff word for word. And in the case of Llama 70B, it's around 80 layers. It's 80 layers, and it'll be around 35 gigabytes. So one thing I could do, if I don't have enough memory to put the whole model, I could just put a portion of the model into memory. So I'll put a few layers into memory, compute that, keep the embedding, and then load it out of memory, load the next like portion of the layers in, and so on. So, and there are a lot of libraries that do this. It's quite simple to code. You could just like say, well, I just want this number of layers into memory, at each point in time, and I will just keep loading stuff in and out of memory. This works, but it'll be like really slow because now I'm just like loading 16 gigabytes in and out of memory to generate every single word. And depending on the model size, you might do this multiple times. So actually, in this example, if I just did this, I would get around 0.3 tokens per second on this specific machine. Obviously, if you have a worse laptop, it'll be even slower. So just like on a high level, I could do all this on one device. I don't need multiple devices. You could just run any model as long as you have enough storage for it. And if it fits in memory, you would just like have very fast generation because you can just keep sequentially generating more words, tokens, like we've seen in the demo. And if it doesn't fit into memory, I can like sequentially load layers in and out of memory. And that's very slow, obviously. And because I have to do that for every single token to generate, it just ends up being very slow in the end, like 0.3 in this specific case. And that's 70 billion parameters. I didn't even try the 400 billion, probably like really, really slow. Maybe a token per minute or something. Okay. So if I have multiple devices, like how would this help in speeding things up? Well, first of all, I need a way to connect these devices. And in the Excel library, just like just the default thing, just like gRPC. I'm just like on a local network, we're all together, and I can just connect via that. But I can also do other things, like get a Thunderbolt or something, and like connect devices together. And if I connect devices together, what I can do then is I can take the entire model, and I can split the layers, and I put a few layers on each device. And those layers are then fixed. I'm not loading anything in and out of memory like I did before. Like each device, in this case, if I have enough devices, it was 35 gigabytes, so I'll put 11.67 gigabytes on each device here. So the portion that each device has fits into memory. And then the only thing I'll pass around is embeddings. So will this be faster or slower? Well, depends. There's a certain cost I have to pay in terms of speed in like loading things in and out of memory, which the problem I had before on a single device. Now that I have multiple devices, the bottleneck is how expensive it is to move things between devices. But when you move these embeddings between different devices, these are like way smaller in size. Like the embeddings of the specific model are around 5,000 parameters, so this will end up being like 16 kilobytes. So the speed I will get here depends on like which one of these two is faster. If I have a really, really, really bad internet connection and the stuff is like incredibly slow, like 1 byte per second or something really slow, then just doing a single device would be better. But for any reasonable internet, this like just transferring a few kilobytes over a network will be much faster. And in this particular setting, obviously it depends a lot on the internet speed, but when I tested this last, you will get around 12 tokens per second versus 0.3. So this is the high-level idea, is like, you could just run most things on a single device, but you'd have to load things in and out of memory, which is very, very slow because it's just very large, and you have to do it like multiple times for every word. You have to do it for every token. But if you just can split the model itself on all these devices, then you can like sequentially just run through the model, pass embeddings around, and process things much faster. Now, a question is, if I have this setup with these three MacBooks, and now I add another phone in here, what would that do really? Like, would it help with anything? So one thing to highlight as well is the model is processing information sequentially. So in this example, when I just have 3 devices, when I have an input that goes to like MacBook 1, and MacBook 1 now has a few layers, it processes something and has an embedding. While MacBook 1 is processing, MacBook 2 and 3 are just chilling, not doing anything. They're just sitting idle. And then the embeddings go to MacBook 2, and then MacBook 2 is processing, and 1 and 3 are just like sitting idle. So in this specific example, because it has just one query, like each just MacBook is just sitting idle. And if I now have add another device in here, and the 3 devices I have before are already enough to like not need to on and offload anything, then having another device will just slow things down. Because now if I just like, let's say, depends how I partition the model. Let's say if I partition the model like according to memory here, now I could have just done it with 3 devices, but now I have to pay this extra cost of like passing every token around to the iPhone, and I'm just like slowing things down for no reason. So if I'm optimizing for latency, I just need like faster responses. Having multiple devices helps me up to a certain point, and then it's just like bad. It just slows things down. Then in this particular setup, a Git partitioning strategy would just ignore the last iPhone. And there are all types of other things that you can take into account here. So actually, we have in our GitHub a bounty to like have other creative ideas for partitioning strategies. But just like on a high level, if two devices have a Thunderbolt connection between them, and the others like are Wi-Fi connected, then that can inform the partitioning strategy because you can move information around much faster on a Thunderbolt, like literal wire, than over like a local network. So just the takeaway I'm trying to give here is latency improves by adding certain devices up to a certain point, but then afterwards it doesn't. What does improve all the time is throughput. So back to the example where I have this phone. If I'm processing like one request, having like 20 more max here does not help me with anything at all. It just slows things down all the time. However, if I have 20 more max and I'm trying to process more requests, then I can like schedule things efficiently such that I'm utilizing the machines better. So I can do like a scheduling type thing like this, where I can have 4 devices and I can split the layers. And after the first device processes the first request, it starts with the second already. And I can just like now like optimize for throughput. And I can just practically, if I schedule properly, like get linear scaling. The more devices, the better. So I can process more requests per second, but every individual request is not per se faster. Yeah, that's the high level thing I wanted to just highlight. Is just like, why is having devices more helpful? And then once you have this core piece working, then you can get all types of different applications and things built on top. So just before I get into these videos, the high-level idea is that you can just grab any hardware you have, and you can aggregate it in a way that's meaningful and run large models. And as I said, like just having more devices typically helps you with latency up to a certain point, because a single device will be really slow, but then you get diminishing returns. But there are other things you can do with these, like this setup. For example, you can optimize for throughput, or if you're doing things like reasoning models, you can just like get faster reasoning by having more devices. And in general, like, what are the properties that you get by just like running stuff locally on devices? Well, one of the things is privacy. Another one is like low latency compared to like going to a cloud and back and so on, like lower cost and stuff like that. And this can allow you to like run things that I personally wouldn't be comfortable running in the cloud. Like if I had an agent that lives on my devices, leaves all my data and gives me recommendations, I would not use like an API to send that, but I would use it here. So just very quickly on how this all works. I already have everything set up, so I'm just gonna like run EXO, and when I run EXO, I gotta set up like this. Well, in my case, only one person so far has installed it, so now the 2 of us are connected. And now I could just like do a bunch of other stuff, like go to my local server and just, for example, like run like a chat. But this is like just a simple bare bones, like just running an LLM. But the more interesting things, for example, are in these demos. First is, what if all my devices aren't all in the same place, like a local network and so on? One nice integration here is tools like Tailscale.
An AI assistant running on a distributed system called EXO, locally hosted large language models, running on the EXO distributed system.
Tell me more about EXO.
EXO is a distributed system consisting of 3 nodes, a MacBook Pro and 2 Mac Studio machines, with a total of 448 gigabytes of memory and 100.
Well, yeah, so basically what's happening here is I have my cluster that's like sitting by itself, and it's not all connected on a local network, and I can just have my phone and be anywhere else, and then like basically use my home network as a cloud. So I don't need to be home to use my phone, but I could like phone and do something else. I could also just like add my phone itself to the cluster and like
Schedule a catch-up with Mo.
like create an app. For example, here I'm just running an agent fully on device, and you can just watch the video.
Siri, schedule a catch-up with Mo.
So this is like a version of Siri that just runs locally, and yeah, you can, I guess, read if you can't hear what it's saying. So I have this open source version of Siri that just runs fully locally on my cluster. It has multiple models in it. One of them is an LLM, so I can talk to it. Another is a vision model, and if you take a look, you see these things called automation running the whole time. What's happening is the model just stops, takes a screenshot, analyzes my phone, and then figures out the right action to take. He was instructed to schedule a follow-up call. So like swipes, goes to my calendar, and well, it does all the action it's supposed to take. And yeah, part of the follow-up is, well, invite the right people, and then yeah, you keep seeing this automation running, which is it stops, takes a screenshot, analyzes with a vision model, and then just keeps going ahead. Oh yeah, and I think in the start of the demo it says also, it asks, do you want me to DM him? And then Alex says yes. So now the model is just like looking after the calendar. It gets the invite and then it finds me, Mo, and just DMs me the link. Which is essentially doing the same thing, like you just do with setting up a cluster, but like the actual application that's running on it is not just a simple LLM interface, it's just something a bit more interesting. And what's happening? Yeah, and then one final thing I just wanted to show is that you really can add anything to these clusters. If it has like meaningful compute, it's just like,
So
it wouldn't necessarily help. So here's an Apple Watch, for example, running a small model called Whisper.
I'm about to travel to New York and I want to go see a basketball game.
So essentially what's happening here is like you just have a Apple Watch and you can run a small voice text model, like a transcription model, and runs fully locally because your watch has a small GPU and an Apple neural engine on it. Well, whether adding a watch to like a cluster of loads of Macs helps, probably not, because as I described earlier, you don't get any more lower latency, you just get more throughput. But that's just like, yeah, I hope that gives like a high level idea, a good enough idea of like what EXO does. You can just, again, aggregate any hardware you have, whether it's like phones, laptops, watches, whatever. You can put it into a cluster, and then you can like run AI workloads on it. And there are multiple limitations, and there are different ways you can go about it, depending on what you're optimizing for. And it's all open source. You can go play with it. Yeah, and that's it. And finally, just want to say that we are hiring at EXO, so if you're interested, you can just check out jobs@exolabs.net, or just go on Twitter and like find me or find Alex or just the company account. So yeah, that's it. Thank you so much for listening and any questions. Yeah, sure.
Are there any questions?
What's the help of a phone? So in terms of comparing to a laptop. So a phone is like a fourth of a laptop, or it's like a 1/10 in terms of computing power provided.
Yeah, it depends on like what phone and what laptop obviously you use. So the latest iPhone 15 Pro Max has 8 gigabytes of memory, and actually my old Mac also had 8 gigabytes. So like in terms of memory, they're the same. My laptop obviously has more flops. It can just like do more processing, and I think will be like the old Mac and the new phone are probably like double or something. Not that big a difference. But obviously, if you go get like a full spec'd out MacBook Pro with an M3 chip, then it's like way more powerful than a phone. And also the watch is just trivial compared to any of these things. So it's relative what you're doing. If you have 2 phones and you add a 3rd phone, it's meaningful. But if you have like 2 spec'd out Macs and add a phone, it's just useless probably.
Touching on that, does it only support software inference, or if there's any accelerator, whether a general GPU or a more AI specialized accelerator, can it leverage that as well?
In theory, yes. The Apple neural engine and the Apple devices is a bit like locked down. You can't do that much with it. So we've managed to like run stuff on the watch and a fair few things on the phone, but you can't really access it much. But in theory, you could just do anything. You can also use the CPU if you want. Wouldn't per se be very helpful to use the CPU in this context, but yeah, you could. One of the things we use in the back end is called TinyGrad, and they support all types of different hardware. So you could just have any accelerator that is supported by the back end be used here. If someone knows how to use the Apple Neural Engine, then please come speak to me afterwards, because there's very little you can do with it as a developer.
Any other questions? No? Okay. Thank you very much.
Thank you.
All systems are nominal. Initialize Genesis